Chapter 4, Displaying Quantitative Data. There are several good ways to display the distribution of a quantitative variable. The most basic is called a dot plot. Here is an example using heights of 50 students. Each dot represents a student and their corresponding height. This student is probably about 57.8 or 9 inches tall. This student is a little over 74 inches tall, etc. Note that it is clearly labeled along the axis and scaled. Dot plots are very good for displaying small data sets. However, when there are a large number of observations, histograms are a better choice. Histograms are similar to bar charts, but for quantitative data. As with bar charts, the possible values of the variable are plotted on the horizontal axis, and the frequencies are expressed as the heights of the bars. However, the bars of a histogram should always touch, indicating that we are not leaving out any possible values. Vertical axes should always start at 0. If not, you can skew the analysis of the data based on the histogram. Since this data is quantitative, there are no natural categories to place the data. In this case, we will define our own categories called classes or bins. There is no perfect way to create bins, but bins should always be the same length and never overlap or leave any gaps. Ideally, you should use between 4 to 10 bins that start and end on nice values. What if an observation falls exactly on a boundary? As a convention, we will put boundary values into the upper bin. For example, suppose you decide on bin lengths of 2 starting at 56. Then the boundaries would be 56, 58, 60, etc. The bin from 56 to 58 would be 56 up to, but not including, 58. Let's go up here and look at that. That means we go from 56 and 58. If we had somebody that it was exactly 58 inches, they'd be in the next one. I've gone ahead and finished dividing my data with bin widths of 2. Notice that right here on the division there's a person that's exactly 66 inches tall. He will fall in here. So there are 1, 2, 3, 4, 5, 6, and 7 students in that bin. I'm going to go ahead and count the rest of the students in each bin. There you go. You can pause and write that in. We're going to use that data to create a histogram. So the first bin had 1 student in it. The next bin had 3 students in it. And I can reveal the rest of it. Obviously, it's a bar chart with all the lines touching. What's nice about it is it gives the shape of the distribution. We could also do a relative frequency histogram, and it happens to look the same as a regular histogram, except that it will have relative frequency, which is the percent of the total, rather than frequency, number of observations, on the vertical axis. Relative frequency histograms are particularly useful for comparing distributions with different sample sizes, since the vertical axis will be on the same scale. So if we go back to our data, we just need to make percents. Well, there was 1 student in here. Turns out there are 49 students on this chart. So 1 out of 49. About 2% of the students live in this bin. If we did the next one, 3 out of 49. About 6% of the students live in this bin. I'll let you do the rest of them and then go ahead and add that to our relative frequency histogram. Notice that now my vertical scale is in percents, and you can go ahead and graph that. Be careful not to make the common mistake of using 1 bar for each observation, where the height of the bar represents the value of the variable for that case. So if you looked, our first person up here was about 57.8 inches tall. People say, okay, that's person 1, and he's 57.8 inches. And they go to person 2, and he was about 59 inches. That is super, super, super wrong. Please don't do that. If you'd like to see how changing a bin width can make a big difference on your histogram, check out this applet. Note, there are methods for creating histograms with unequal classes, but we are skipping them. If a frequency distribution has non-bounded classes, such as 12 or more, a histogram cannot be made. Now we're going to talk about a stem and leaf plot, and we know that's another way to display relatively small numerical data. In a stem and leaf plot, the stem is the first part of the number and the leaf is the last part of the number. Okay, we did this in class with the game Agreed, so I just have this example for you. Make sure that there's a key also. Okay, make sure you label everything. The leaf should be single digits. And it's best, but not mandatory, that the leaves are in numerical order. Remember, they look very much like a dot plot or a histogram, but they preserve the actual data, because above we had to guess how tall people are. Here we know exactly how much these sophomores weigh. We could also do a back-to-back stem and leaf plot like we did on day 1 with Game of Greed in order to compare. If you wanted to compare these sophomore female weights, you could put them on the other side of this over here, but I won't make you do that unless you want to. There are a couple other types of stem and leaf plots. The first one happens when the data is very compact, in which case we might want to truncate to stretch the display to investigate the shape. Notice if we're talking about body temperature, 96.3 degrees, 97.6 degrees, there's not a wide range of body temperature. If you get too hot, you die. So you can look in our display here, it's kind of compact. Instead, if we split each stem into a low and high value and regraphed it, with this one being from 96 less than or equal to 96.5, and I should say less than but not equal to, and then this one being 96.5 up to but not equal to 97, we actually see there's a gap in our data where nobody was measuring their temperature, so it gives us more information. The other way to do it, and it looks like this word should have been split, excuse me. Careful to split the data. Down here we would want to truncate the data, which is the opposite. It's too spread out, and so right here we have 10.53, and in order to get to the next one we'd have to have a super long stem and leaf plot. Instead, if we just went ahead and got rid of the 3, we didn't round, we just truncated it, now we have a spot. The next one on 13.67, if we just truncate it, it makes it more condensed. The next thing we're going to talk about are 4 key features of a distribution, and these are super important, and they are shape, center, spread, and unusual values. For this lecture, we'll only talk about shape and unusual values, and there are 6 shapes we'll talk about. You've probably seen these before. The first is bell-shaped or symmetric. The next, left skewed or right skewed. Remember, left skewed means the majority of the data is on the right, with 1 or 2 or a few outliers pulling the data to the left, and vice versa for right skewed. We also have single peaked or unimodal, which means one bin of data that has the most data in it, or double peaked or bimodal, where we have 2 bins of data that are about the same and they're both the highest, or uniform, where most of the data is the same. Finally, let's talk about unusual values. There is no specific definition of unusual values, but there are some things to consider. We have outliers, which are when data values fall out of the pattern with the rest of the distribution, and later we'll learn how to define something as an outlier. We'll give a specific definition for that. We also have clusters, where data is grouped together, isolated by itself. And then we have gaps, or large spaces. Here's an example of some runners' times, and most of the data is kind of symmetric. It's over here. And then we have 2 runners that are just super, super fast. Those are the outliers. You never want to ignore the outliers. They're extremely important. In fact, this one's Usain Bolt. Well, we know he's just scary fast. Here's another example. All outliers should be taken seriously and should be investigated thoroughly for explanations. Atomic outlier rejection schemes, such as to throw out all the data beyond 4 sample standard deviations, are particularly dangerous. We'll talk about that later, but here's an example. The classic case of an automatic, and I said atomic before, but I meant automatic, outlier rejection becoming automatic information rejection was the South Pole ozone depletion problem. Ozone depletion over the South Pole would have been detected years earlier, except for the fact that the satellite data recording the low ozone readings had outlier rejection code that automatically screened out the outliers and didn't report them. Such inadvertent and incorrect purging went on for years. It was not until ground-based South Pole readings started detecting low ozone readings that someone decided to double-check as to why the satellite had not picked up this fact. It had, but it had gotten thrown out. And we want to say this: the best attitude is that outliers are our friends. Outliers are trying to tell us something, and we should not stop until we are comfortable in the explanation for each outlier. And yes, sometimes outliers are errors, but not always. Please fill in the rest of your notes.